Your lesson on probability rules. This is the second video in a 3-video series on this topic. In part 2, here we are going to look at independent versus dependent events. Let's define those first. Independent events are events for which the outcome of one does not influence the outcome of the other. For example, let's say there is a 10% chance you will put a hat on in the morning, and then there is a 80% chance your bus will arrive on time. Whether you put your hat on or not has no influence on the probability of your bus coming on time. Those events are independent of one another. Dependent events are the opposite. These are events for which the outcome of one does influence the outcome of the other. For example, let's think of an example. Let's try this example. When that bus arrives, you get on the bus. Let's say the probability you say hello to the bus driver is 20%. The probability they will say hello to you probably depends on whether you said hello first. So if you say hello, the probability they will say hello is probably 90%. If you do not say hello, the probability they will say hello to you is probably much lower. So those are dependent events. Let's look at some examples of that. First of all, let's go back to rolling dice. So we have two dice here, a blue one and a red one. And as you may remember, this is a sample space diagram. It shows all the possible outcomes. For example, if you roll these two dice, you can roll a 1 and a 1. The result is 2. That happens once. Or you could roll a 1 and a 3, for example. The result is 4. So now there are 36 different options when you roll two dice. For example, 6 and 6 is 12. And then we talked about this. 7 is very likely because there are many combinations that make 7. 1 and 6, 2 and 5, 3 and 4, and so on. So that's this whole sample space. The question is, what is the probability of throwing a double 6 with two dice? Well, looking at this diagram, double 6 would occur here, and there it is. Double 6 produces a 12. And there's only a 1 way out of 36 options for that to occur. So we know the probability is 1 out of 36. But today we're going to break that up into its components. One way to look at events like this, where something happens and then something happens right after, even though you think of two dice as being rolled at the same time, you can think of it as rolling one die and then rolling the next die. So it's like one thing happening after another. So we are looking for the probability of rolling a 6 on the red die, then the probability of rolling a 6 on the blue die. And a probability of rolling, whenever you see the word then, or you're thinking of one event then another, in probability that means multiplication. So probability of rolling a 6 on the red die is 1/6. So on this one, to roll a 6 is 1 out of 6. And also on the blue, to roll a 6 is 1 out of 6. When we say this happens and then this happens, we multiply those and we get 1 out of 36. So you can see by the way we looked at this in the past was looking at this as one option out of 36. But now we're looking at it as a formula, a way to look at probability where two events happen one after another, with the result being the same. All right, let's take a further look at that. We have probability of rolling a 6 is 1 out of 6 on one die. Then probability of rolling a double 6, we just talked about, is rolling a 6 on one and rolling a 6 on another. So this, then this, multiply 1 out of 36. Probability of rolling a 6, then a 6, then a 6 would be 1/6 times 1/6 times 1/6, and we can see it is this value here. So what do you notice happening with these probabilities? Well, hopefully you saw that the probability gets smaller and smaller. The chance of the same thing happening over and over again is a small chance. And there is a formula for this, which you should write down. Again, with these videos, in this series of 3 videos, there are notes pages that go along with it. Please print those and take some notes. So for independent events, when we have the situation of probability of one thing, then another, we just multiply those probabilities. Using our probability symbols, we can use intersection to represent that. So it's A intersection B intersection C. So A, then B, then C, which basically means A has occurred and B has occurred and C has occurred. We just multiply those. Okay, simple formula, but important. So let's take a look. So now we have an example of a box of chocolates, which contains 12 chocolates of 3 different types. There are 3 strawberry, you can see them here, 4 caramel, and 5 milk chocolate. Sam, this guy right here, chooses a chocolate, then puts it back. All right, So don't worry about whether his manners are good or not. Clearly, those are bad manners. You don't just take a chocolate and put it back, or even worse, take a chocolate, take a bite, and then put it back. How terrible is that? But we're not here to morally judge Sam. We're just trying to look at the probability. So he puts the chocolate back. Then Jenny does the same. Calculate the probability that they both choose a strawberry chocolate. So he takes the strawberry, takes a bite, puts it back. Then Jenny chooses from the same box. What is the probability they both have selected strawberry on that first choice? So we're looking for probability of strawberry, then strawberry, like strawberry chosen by him, then another one chosen by her. Let's take a look. That should be 3 out of 12 because there's 3 out of 12 strawberries. And then that one goes back in the box, and then she has 3 out of 12 again that are possible strawberries because he's replaced the box back to its original set of chocolates, right? So that probability, multiply those, each of those is 1/4, so that becomes 1/16. Now let's flip this problem around a little bit. Notice everything stays the same except for the bolded and underlined text. In this scenario, Sam now has some manners. Instead of putting the chocolate back, he eats it. Whether he likes it or not, he's going to finish it because he took it. All right, so he grabbed the chocolate, eats it. Now Jenny reaches into the box and grabs the chocolate as well. We're looking for the same situation. What's the probability they will both choose a strawberry one? Now, since he's eating one, has the probability they both choose a strawberry gone up or gone down? What do you think? Well, the probability of them both choosing strawberry has gone down because essentially he has eliminated a strawberry from the box. So now her odds of getting a strawberry have gone down significantly. Let's take a look at the numbers. So probability of a strawberry chosen and then another strawberry chosen. So we have his probability with the full box, 3 out of 12 are strawberry. Then, so we multiply, and now this has changed to 2 out of 11. That's because he took a strawberry and kept it, ate it. Now there's only 11 chocolates left, so that's that 11, and only 2 of those 11 are strawberry. So her odds of getting a strawberry are lower than his were. So when you multiply those, it's 1/4 times 2 11ths, you get 1 over 22. Before the chances were 1 over 16, now it's 1 over 22 chance that both of them will get strawberry. Again, that makes sense because he has reduced her odds of getting a strawberry. This is an example of a dependent event, whereas the first one was independent because his action had no influence on her probability, right? His action, he reset the box by putting it back. So she gets the same original box as he got. So her probability is unaffected by his action. But in the second situation, his action does affect her probability. His action changes the makeup of the box. Therefore, her probability is now dependent on his action. So that's a dependent probability. Okay, let's take a look. There's some formulas that go with this. So for dependent events, when we think of something like A then B happening, we call that an intersection. A has happened and B has happened. And the formula for that is probability of A times probability of B. And this means given that A has occurred. Okay, so a little bit strange at first, but basically it means exactly what we just saw. The original probability, imagine his probability of getting a strawberry chocolate, and then multiplied by her probability of getting a strawberry. However, her probability, given that, means her probability is adjusted based on the actions or the results of this thing here. So looking back at an example we saw a few days ago, we have this table of information. It is the age distribution of prison inmates by gender and also by age. Let's look at part D here, and then you're going to try a question on your own. So the prisoner, we're looking for the probability the prisoner was 19 or under, given that the prisoner was male. So now notice that this has given that in it, and that's what we see here, given that. So this probability we're being asked is actually a probability of this form. Let's take a look. Here are the prisoners that are male, that are 19 or under, given that they're male. So these are the 19 or under males. So our probability here, we can say for this one here is the probability that we have 19 or under given that it is a male. So we're not looking for all these 19 and under, we're looking only for the 19 and under in the male category. So there's dependence there. We first looked at just the male group and then we find 19 and under within that group. That's dependence. And that number is 451, the sum of those, divided by only the males. All right, so it's those ones out of the male group only. and it gives us that. So that's something we kind of looked at already, but now let's take a twist on that and ask this question. Find the probability of somebody chosen from this group being a male and being 19 and under. Now that you've tried, let's take a look. What this means is we're going to use this dependent event formula. So we're going to have probability of first choosing a male times the probability of choosing somebody 19 and under, given that we have chosen a male. So we're using this formula. All right, let's take a look. Probability of getting a male is 4,822 out of the whole group of people right here. And then we multiply by the probability of choosing somebody that is 19 and under, given that we're already talking about just the male group, right? So 451 out of this group here, which is what we had here. Notice these two here, we have this numerator and this denominator the same number, so we can cancel those numbers, and we end up with 451 over 5,036. That is our answer to this question. And it should make sense because if you looked at it before you even use this formula, if we're looking for prisoners that are male and 19 and under, well, these are the prisoners that are male and 19 and under out of the whole group. All right, prisoners and male 19 and under out of the whole group, and that's the answer we got here, 451 out of the whole group. So this idea, if it's the first time you're seeing this formula and these ideas, it's a little complex. I would say pause the video and just think about this symbol and how we used it here and what this number represents and all that. So take a look. Let's try a few examples as well. So here's going back to the chocolate problem. We're going to add the proper probability symbols. So first of all, strawberry, then strawberry. So I put probability of, this is not Sam, this is strawberry. Strawberry chosen, sorry, this is Sam. Sam chooses strawberry and Jenny chooses strawberry. And then written here, it would be probability of Sam choosing a strawberry times probability of Jenny choosing a strawberry. And we saw that there was no dependence there, so independent probability, they're the same. Now in the second example where there was dependence, the original statement has to change. Probability of selecting a strawberry for Sam and probability of Jenny choosing a strawberry given that Sam has chosen a strawberry. Okay, so this has changed here. Now it is dependent. And over here we have the probability of Sam choosing a strawberry and the probability of Jenny choosing a strawberry, given that Sam has chosen a strawberry. So again, her probability has been influenced by Sam's selection. Okay, so next we have this last problem for you here. Peter has 10 colored cubes in a bag. Again, everybody walks around with a bag of cubes at all times. That's just what we do in real life. So please grab your bag of cubes as we do this problem. All right, so we have this bag. There are 3 red. Sorry, the cubes are 3 red, yes, and 7 blue. This person, this is Peter, I guess, removes a cube at random from the bag, notes the color, and does not replace it. So when he takes it out of the bag, he keeps it. He then removes a second cube. So is this independent or dependent? Well, hopefully you're thinking this is dependent because his first action changes the outcome of the second. Now it says calculate the probability Peter selects a red and a blue cube in any order. This is a key statement. So see if you can calculate this. Okay, let's take a look. All right, so in any order means he can take a red then a blue or a blue and a red, right? The only condition is that there's one blue, one red. So it could be red first then blue or blue first then red. So either this or this happens. Let's break this down to symbols. We have probability of red followed by blue or blue followed by red. That's what we want to find here. And that can be written more in using our symbols. Probability of red then blue, so red and blue, or probability of blue and red. Okay, so the order is important here. Let's take a look. Probability of choosing a red is 3 out of 10 cubes, and then and here means multiply. Blue is 7 out of 9. Then you add the probability of doing blue then red. Oh, by the way, why did this go down, right? Because he kept a cube. So once he took one out of it, there was only 9 left, but there was still 7 blue left. Over here, he originally takes a blue 7 out of 10, but then multiply by 3 nines because there's only 9 left and 3 of them are red. Check the final steps. these two end up being the same, and our answer is, oh, let me go back to it. Answer, hope you were able to come up with that. If not, study this carefully.